Yeah, good morning to all. In this session, we are continuing with the minimum mode system with its timing diagram. So, as we have seen in the previous session, that this is the system which we require to design in order to operate 8086 microprocessor in minimum mode. So, minimum mode nothing but 8086 is the master, is the controller. So depending upon these pins, these controlling pins for reading or writing operation from memory or IO devices, and for selecting the RAM or ROM, high, even or odd, high or low order memory bank. ALE is being used for removing the address line separately in the latch. So as it is 20 bit, so we require 3 latches in order to store a 20 bit address. Similarly, DN bar and DT by R bar, these are the two control pins which controls the data which are being multiplexed, which are being demultiplexed from the AD0 to AD15 as D0 to D15 by using two transceivers, as we require to store 16 bit. So we require two 74245 which are 8 bit transceivers, D0 to D15. Okay, so depending upon BHE and A0, as we all know, A0 and BHE bar are the controlling pins for selecting the RAM and ROM. So out of which the selecting RAM, even order, odd order, even order, odd order. So depending upon this one, it will take that address from the RAM, the address of the instructions from the latches, and takes from the RAM and do the operations with the help of data being present. And depending upon the memory read or memory write, it will do the read operation or write operation, IO read or write bar. So what I have discussed previously is the same thing. In your minimum mode 8086 system, the microprocessor 8086 is operated in the minimum mode by making MN by MX bar pin to logic 1. In this mode, what the thing is, all the control signals are given out by the microprocessor itself. So there is a single processor in the minimum mode system. The remaining components are latches, transceivers, clock generators, memory and IO devices. So first, clock generator, what it does, it gives the clock signal which synchronizes with your external signal with the system clock. Getting a point here? So whatever the clock generator generates the clock that is synchronizing with your system clock. Next, it has 20 address lines and 16 data lines. So 3 octal latches and 2 octal data buffers, or I can call as transceivers, for your demultiplexing address and data buses. Latches, they are normally that latches are D type flip flops, nothing but data flip flop, nothing but they can be able to store only the data. So whatever the data we are getting from our ALE, it will be stored in our latch. Transceivers, they are bidirectional buffers which can able to read the data, write the data. So sometimes they are also called as data amplifiers. They are required to separate the valid data from the multiplexed address or data signals. They are controlled by two signals which are called as DEN, data enable, and data transmit or receive. Data enable indicates the availability of valid data over the address or data. Data transmit or receive signals indicates the direction of data. whether it is from or to the processor, whether the data is being transmitting or receiving, whether it is source or destination. So usually EEPROM are used for monitor storage, which is one of the type of ROM, while RAM for users program storage. So these are the minimum mode pins which we have discussed. Okay. So these three are the selection lines through which you can able to tell, as we have used here. I guess 3 to 8 decoder. So these three are S2, S1, S0. Depending upon this, the selection lines, it will operate. When they do these three are zeros, it's nothing but interrupt acknowledge. Interrupt has been occurred and acknowledged and should be acknowledged. 001 IO read, 010 IO write, 011 halt, 100 opcode fetch, it fetches the opcode, 101 memory read, 110 memory write, 111 not active. So these are the status pins which is useful for your 3 to 8 decoder, which performs depending upon the selection lines, to read or write operation, or interrupt has been occurred, or taking halt, or whether it is active or inactive. Queue status, we have 2 pins for the status of queue, because in our microprocessor we have instruction queue which is being storing the instructions while fetching is going on. So when QS1 and QS0 are status, when both are low, which means there is no operation being done in your queue status. So whatever was being done in the last clock cycle will be same in the queue. So when 01 is being applied, nothing but the first byte is stored into the queue for decoding part. So first byte will be stored in the queue. If it is 10, the queue is empty. If it is 11, the next byte or next subsequent byte will be stored into the queue. This is how your queue status pins will perform while storing the 6 byte instructions in the queue. So this is the timing diagram for when 8086 microprocessor will be operated in minimum mode. So when clock is being applied, suppose we have some clock cycles T1, T2, T3, this is the waiting, TW, T4, so on, as 4 clock cycles are required for the next transition. So ALE, address / enable, for 1 clock pulse, it is on. Nothing but when it is on, the addresses should be enabled. The address will be stored. So add or status, you can see here, during this timing pulse, BHE is giving as A19 to A15, which are status pins, which is S3 to S7. Then the next cycle it continues. For the data A0 to A15, because why they both are separate? A0 to A15 is being multiplexed with the data also in our AD0 to AD15, whereas A16 to A19 are separately for address, which are taking as your status. So during this clock, ALE is enabled. So this address will take address from the data and it will read the data from the memory. Depending upon the data enable or data transmit or receive, it will read from the memory or from the IO bus. So you can see here A15 to A0, then this is bus reserved for the data in as they are low, as your read bar is low. If it is high, read bar nothing but when it is low, it is enabled, so it is reserved for your data. Similarly, data enable bar low and data transmit or receive bar is also low, because we are going for read cycle. This is the read cycle for read bar, data enable, data transmit or receive. So if it is low, R bar, it will receive the data. It is not transmitting, it is only reading the data whatever you are getting from the processor. This is the timing diagram of your minimum mode 808 system only for read cycle. They are clearly given here. Next, write cycle. How your write cycle will be for minimum mode. The same clock pulse we have taken here, T1, T2, T3, TW, T4. Again, ALA is enabled, same. So now, as your write bar is low, nothing but active low, this write bar is enabled. At this time, at this period, your data will be written into the memory or into the IO. With the help of, the data enable bar should be enabled in order to enable the data to write it or read it. And data transmit or receive bar, here I need to transmit the data, so it should be 1. So these are the signals, these are the control signals in order to enable the write operation either to memory or to the IO bus. Clear? So in the next session we are going to discuss maximum mode.